So, today I'll present a paper about deep heat model, which introduces deep neural networks instead of relying on rigid mathematical assumptions. Before starting, let me quickly mention about some key concepts in our lecture. In the lecture, we've studied censoring, survival curves, and Cox's proportional hazard assumptions, and so on. And because they will reappear throughout the talk, so please remember. Historically, survival models share a three-step structure. First, they assume a specific form for the underlying stochastic process. Then, they learn how covariates relate to its parameters. And finally, they derive the distribution of first hitting time. While they works in some situations, but these parametric assumptions are often violated. Also, the three biggest limitations are strong parametric assumptions, as I mentioned, and time invariance, and inability to handle competing risks. This figure shows the time invariant with under proportional hazard assumption. Two log hazard curves stay in parallel with constant gap, so it means the covariate effect is time invariant. Also, even neural network approaches only relax the covariate to hazard mapping and keep the proportional hazard assumption intact. This paper argues that deep heat introduces a paradigm shift. As the diagram shows, while traditional methods takes that long and indirect route, deep heat maps covariate to distribution directly using neural network. So all intermediate assumptions are eliminated. So how does it solve three problems I mentioned? The first two problems, parametric assumption and time invariance, can be solved simultaneously and directly by neural network. Because neural networks learn the joint distribution directly without explicit model assumption, it can solve them. And inability to handle the competing risk can be solved by multi-task architecture, which captures how different risks might interact with each other. Next, before introducing the model structure, let's formalize the data. For each patient, we have a triple consist of X, S, and K. First, X is d-dimensional covariates, and S is the event time or censoring time, which is discretized with finite horizon Tmax. And K is one of K causes, or it can express by empty set symbol if the patient is censored. There are three assumptions for this model, and the first one, discretized time with finite horizon, seems trivial in practice, but the third one, right censoring occurs completely at random, seems non-trivial, and hence I think it is one of the main limitations of this model. The learning goal is simple. Given covariate X, estimate joint distribution of event time and cost. Unlike the previous models that only modeled the hazard, deep heat directly handles this jointly distribution of time and cost. The table on the right shows the example data set, and there are covariate, censored, or even time and cost. Next, introduce the model architecture. To handle the competing risk, it is modeled by specialized multi-task network. Input, a covariate X, first passes through the shared subnetwork that captures a common representation across all causes. And this output, Fs, is combined with original input S, X, and fed into the cause-specific subnetwork. There are k number of such subnetworks, and hence each branch learns cause-specific refinements. Here, we need to include the original X to the subnetwork together to prevent the loss of cause-specific information that might not be captured by this shared representation. Next, the single softmax output at the top. The output is a matrix of size k by tmax, which is normalized so that all entries sum to 1 throughout a single softmax. This ensures the model learns the joint distribution, not marginal. Each cell value is the estimated probability that event of the cause occurs at the time. Next, introduce the cumulative incidence function, and so-called CIF. For a cause K and covariate X, CIF is the probability that the event of cause K occurs by time t. Formally, it's just the sum over all timestamps from 0 to t, the probability of such event at time step. Also, there is one remark. By adding CIF with respect to K, we can obtain a survival curve given X. You can check this simple derivation process here. Then, how do we apply this definition in DeepHit model? Obviously, we cannot directly compute CIF, and we need estimation. Since the softmax output already gives us the probability at each time for each cause, the estimated CIF is simply the replacement of P to P hat, and it is just taking a sum of softmax outputs over time. This estimated CIF plays an important role in the loss function on the next slide. Now, observe a loss function. The loss function is defined by a sum of two terms. The first term is the log likelihood, which fits the distribution to data. And the second term is the ranking loss, and it guides the model to correctly rank patients by risk. And each L1 and L2 are defined by such a bit complicated formulas, but we'll observe some intuitions of these functions from the next slide. Looking at the first term in detail, the two indicator functions can be separated by uncensored and censored parts. The figure on the right shows this intuitively. Think of the K by Tmax grid as a mailbox. For an uncensored part, we can maximize the probability of exact correct cell. This is the standard categorical likelihood. However, for a censored patient, we don't know the true cell. The event might happen or not, and all we know is that the patient survived at the time S. So we maximize the probability of any event happening after S, which is 1 minus the sum of cumulative incidence function. And as we observed and derived in the previous slide, it is the survival curve. In the figure, that's the sum over all cells after the censoring time. This way, censored patients still contribute their partial information to learning. Now, the second term loss. Since this term uses the concept of acceptable pair, we need to define it first. For cause K, a pair ij is called acceptable if this indicator function is 1. Intuitively, if patient I experiences cause K at time Si, while patient J was still alive at the time. Also, there is a function eta, which takes the difference between two CIF and passes through exponential. The 3D plot on the right shows its shape. On the right, at y equals x plane, the true patient CIF exceeds the comparison patient's. Eta is small, so the loss becomes small. However, if the true patient CIF is smaller, the loss grows exponentially. Intuitively, this penalizes the model if the patient who died earlier is assigned a lower CIF than one who lived longer. The figure shows the full training flow as a computational graph. Input X goes through the shared subnet, and its output Fs combined with original X forms Z and fed into the cause-specific subnets. And the softmax Y is the softmax output. The labels, each patient's cause and time, go through fed into the loss block. During training phase, the network uses these labels to calculate indicator functions, identify acceptable pairs, and calculate the loss function corresponding to X. The gradients of this loss then jointly update to all parameters across the subnetwork. Now, move on to the evaluation metric. To evaluate the performance, we use the time-independent C index, called CTD. Compared to the original C index, the difference becomes a bit clear. The ordinary C index uses a single risk score R hat, assuming a time independent. This works under proportional hazard assumption, but fails without such assumption. In contrast, CTD uses CIF evaluated at the time when the patient experiences the event. So, we compare risk at the actual time of the event. This makes it meaningful even when risk changes over time. Note that under proportional hazard assumption, the hazard ratio is constant over time as we observed, so CIF curve never crosses and rankings are identical at every time. That's why the two metrics, CTD and original C, coincide under proportional hazard assumption. Also, observe the question on the bottom. By placing the second loss term and CTD index together, we can reveal one important fact. Both are weighted by the same acceptable pair indicator, and both are built from comparisons of CIF differences for those pairs. CTD counts correct orderings with hard indicator. The second loss term penalizes wrong orderings with a smooth and differentiable function instead. So the two share same ordering objective, so-called the patient who died earlier should have the higher CIF. So far, we've observed the mathematical formalizations and now move on to experiments. In this experiment, 4 data sets are used. Among them, the most important one is SEER dataset, which is the only real clinical dataset with competing risks, and hence it is the main task of DeepHit's contribution. Also, while the first 3 are real clinical datasets, the last one, synthetic, is generated artificially. with deliberate quadratic effects in covariance. Since it is designed unfavorably to linear models, I think it is quite an unfair benchmark. Let's look at results for SEER dataset. There are 3 observations. First, nonlinearity matters. Linear models such as CS, Cox, and Fine Gray just stuck at small CTD index, but we can observe that DeepHit reaches the higher score than linear model, so we can conclude that nonlinearity matters. Second, no assumptions wins. For example, BMGP is a model with Gaussian assumption, reaches at CTD index about 0.742, and DeepHit, which has no assumption, reaches 0.752 CTD. There are small gaps, but it is consistent. Third, the ranking loss genuinely helped. By letting alpha 0, which removes the ranking loss, drops 1.0 to 1.6 percentage points. The ranking losses value is measurable. The paper shows an honest note is that for CVD, the gain over CS Cox is not statistically significant. DeepHit shines mainly where nonlinear and non-proportional hazard structure, and this breast cancer is that the case. Next, observe the result for remaining 3 datasets. Observe synthetic first. As I mentioned, synthetic datasets utilizes the quadratic terms, so linear models shows worse performance than DeepHit. DeepHit outperforms them. And on the right, single risk datasets, UNOS and MetaBrick are single risk datasets. While the main contribution of DeepHit model is competing risk, but it also outperforms the other models in single risk setting. In reflection, DeepHit's strengths are lack of parametric assumptions and its multitask structure for competing risk. However, limitations include need for time discretization. While it is trivial, but it forces the beam size as a hyperparameter. Also, it assumes censoring is completely at random, and it cannot handle the recurrent events. Also, the experiment uses datasets only related to medical scenarios, and hence we cannot guarantee its generalizability to other scenarios. Finally, again, synthetic datasets is designed in DeepHit's favor. Before finishing the presentation, there are key takeaways. First, fewer assumptions, more performance. By directly learning the joint distribution, DeepHit removes the assumptions on stochastic process and proportional hazard assumptions at once. Second, the architecture mirrors the problem. The shared and cost-specific structure naturally handles competing risks, and the single softmax forces a joint distribution rather than marginal. Third, the loss design optimizes what we evaluate. As we observed, the second loss term L2 and CTD index aligns, and such alignments makes this model works well on CTD setting. Thank you. It is the end of the presentation.